Now, when we talk about infinity here, we're talking about going all the way up and down and all the way left and right. We're talking about both horizontal asymptotes and vertical asymptotes. Okay, so we dealt with both of these a lot in Math 4. So this is the using the limit notation to get to expand on these ideas. So they threw it into section 2.2. Okay, so if you look at a function like e to the x or 2 to the x or anything like that, as this function goes left, you're going bigger and bigger negative numbers into an exponential. 2 to the e to the negative 10, e to the negative 20. It's going to flip it, and it's going to get smaller and smaller and not equal 0. Now, even though as you go this way it goes up, this is still considered a horizontal asymptote. Okay, even if it's one direction. But the limit as x approaches positive infinity is positive infinity. It's going to go up. Then let's look at this function right here. Sine x over x. What is the limit as x approaches 0 of sine x over x? The limit as x approaches 0. 1. That's from yesterday, yes? The limit as x approaches 0 of sine x over x is equal to 1. Well, now we're asking a different question. What is the limit as x approaches infinity of sine x over x? And what's that equal to? Well, if you graph it, or if you look at the picture here, just kind of think about what's happening in the equation. Again, these are functions that tend to pop up on quizzes from time to time. This neat little sine x over x. And without a calculator, you just have to think about what's happening to that numerator as x gets really big, and what's happening to the denominator as x gets really big. What is the limit as x approaches infinity of sine x over x?
0.
Yeah. Does that make sense? The sine value is only going to go oscillate between -1 and 1. That's all it can do. That denominator is going to get really, really, really big. So it is going to oscillate between positive and negative values, but it's going to approach 0 as you go right. What about the limit as x approaches? Yes?
But it seems like it's crossing that.
And it is. And does that make sense? Why? For example, this sine, it's always going to go between -1 and 1. And it's going to go, every 2 pi it's going to cycle itself, so every 6.28. So that means when x is like 100, or whatever, like this could be a positive, whatever. But then when x is like 110, this would be like the negative value. So when you have the negative divided by a positive, it's going to go negative. Does that make sense?
So it can.
This is going to go like, instead of going here, it is going to go back and forth on it. Because this, as you go right, is going to continually be positive and negative. And your numerator is going to stay positive. So with that fraction, when you divide it, when you have the positive divided by a positive, it's a positive. But when you have the negative divided by a positive, that's a negative. Yes?
So the only thing I was confused about is like in that column, you never touch the limit.
Yes.
But in this one, you can touch the limit.
Yes. Yeah, we'll see. That's a great question. Actually, we're going to look at problems like that later. You can touch a horizontal asymptote, which is different than a vertical, right? We're scared of vertical asymptotes. Like we draw the dashed line and everything, which we'll get to in a second. With horizontal asymptotes, it's nothing bad. It just tells you where the function goes towards. That's all it tells you. Okay? So in this case, you can't touch it. You're going to touch it quite frequently. Every time the sine is equal to 0, which is every pi and 2 pi, or every 3.14, 6.28, and on and on and on, this thing's going to equal 0. And going to the left, it's going to be the same thing. The limit as x approaches negative infinity is also going to approach 0. Okay? And the rules we looked at for limits, the limit as x approaches 2, whatever, the same rules apply. Meaning if you want to know the limit as x approaches infinity of this, that's the same as the limit as x approaches infinity of the first piece plus the limit as x approaches infinity of the second piece. Okay, Anna? So what that's helpful is, okay, what's this equal to? 0. Now what is the limit as x approaches infinity of 3?
3.
What's the limit as x approaches 7 of 3?
7. 3. 7.
Here's where we got like, what is it? What is it? Well, let's draw up a line.
Oh, 7.
The limit as x approaches 7 of 3. Yeah, and that's why we went over this one yesterday. This one's going to come up and we're not going to like it. Here is the f of x equals 3 graph, the horizontal line through 3. At x equals 7, what's the limit equal to? 3. Yeah, it's always equal to 3. Does that make sense? And it's something that just we're not going to like. But this is equal to 3. The limit as x approaches 7 of 3 is 3. The limit as x approaches infinity of 3 is 3. Okay? Okay. So these are some of the properties of horizontal asymptotes. Now from the summer packet, we saw those 3 separate cases. And we're going to see more examples of that today. The 3 cases are when you have your numerator with a bigger power than the denominator. When you have something like x cubed plus x minus 5 over 2x squared. When you're talking about end behavior, when you want the limit as x approaches infinity, when you want x getting really, really big, what's going to happen is the highest powers are going to take over. In this case, the x cubed on top and the 2x squared on the bottom. So, and not around 0, not for small x values, but for really, really big x values, if you're cubing a number, that's going to have more power than just adding that number. So this is going to be modeled the same as this is, without the extra stuff. And then you can simplify. You can cancel out some x's. So this is going to be the same as 1/2 x. So on your calculators, graph this function. Graph that on y1. And on y2, just graph 0.5x. Again, make sure this whole thing is in parentheses. If you got the new operating system, hit alpha y equals, and it'll give you the little fraction thing, so you don't got to worry about parentheses. Does that make sense what I'm talking about? The fraction without any parentheses. X cubed, it also puts in exponents for you. Plus x minus 5 over 2x squared. And then on y2, put 0.5x. So weird stuff happening, but then it just kind of takes off. And then there's the line 0.5x. As you go right and left, that 0.5x is a good model for this function. Again, not around the origin, not for small. 5 is going to do something. But for really, really big x values, you see how much it already took over, even by the time x got equal to 10? Do you see that, Wayman? So it's a good model. So whenever the top is bigger than the bottom, you're going to get some function that's going to model it. Make this change and let me know what happens. If this is x to the 4, cube over x squared, this is going to be what over here? X4? Yeah. Which is going to make this what? X to the 4 over x squared. How many x's are going to cancel out? There's 2 of them. So you're left with 2 on the top. So what does that mean? What that means is this function, whatever this thing looks like, I know the end behavior is going to look just like a parabola for really, really big x values. And take a look at it. What's happening in it? Let's graph that.